Alright, in this video we're gonna make a what's called Lora. It is low rank approximation, and we're gonna have it replace. We're gonna use the image neural net example, and we're gonna use it to replace our first layer dense. And we're going to replace that with a Lora layer. First thing we're going to do, let's see, we'll start with this. So one thing we'll add in is let's call it rank variable. We'll make the rank 4. And we're going to end up replacing this first layer. But yeah, you can do this now, you can do this part later, but just following along, you can put it here. And then we'll come back over here to where we got the dense layer. And we'll just put it right here. Okay, so Lora is basically, let's see if I can explain this. I don't remember how you do this. There we go. Okay, so a normal dense layer, you'd have like X. So you'd have like a 4x4 for a normal dense layer, which would be like that. And in a Lora layer, you would approximate this 4x4 with something smaller, with 2 smaller matrices. Which would be like, and you would do the dot product of them. So that would be the first matrix. And then the second matrix would be like that. So that you would do dot product between this one and this one to get, well, my bad. Or 3, so it's a 3x4, so you'd have a 3 and a 4. You could also, this rank variable right here will decide how many goes in between the two. So this would be rank 1. This would be, since there's 1 column here, 1 row here, it's rank 1. To increase the expressivity of it, you could make it a 2 rank. Which would make both of these 2 rank, and then you multiply those because the number of columns matches the number of rows. Yeah, so that is basically Lora. The weight matrix here that you usually use as a dense matrix, you're going to approximate it here with these 2. Saves on computation usually, because usually it'd be like I don't know, you could use a 50, well, it'd be the number of inputs times or by the rank, and this would be the number of, or this would be rank by the number of outputs. So let's say you wanted to have like 50 neurons. Your second matrix here would be a 2 by 50, which is a lot smaller. And okay, so let's say you have 3 samples like this. You use rank 2, you'd have 3 by 2 here. Let's see. No, it'd be the number of inputs would be, because it's number of inputs here, number of outputs there. So number of inputs would be 3. 1, 2, 3. Your rank would be 2, so it'd be a 3 by 2. If you had a number of neurons of like 50, this would be a 2 by 50. If you had a lot of inputs as well, like for a language model, you have an embedding dimension of 64, let's say, then you could have this as a 64 by 2, which, yeah, you could think would be still quite, I don't know if you think that's large. No, that, yeah. So 64 by 2 would make 128 values versus this, which would be a 64 by 64. This could, for like a language model, this would be a 64 by 2 and 2 by 64. So that's 256 total values with rank 2, whereas this would be 64 squared, which is a lot, big number. But yeah, so that's how Lora works. Usually they use it for fine-tuning language models. But we're gonna, just to see how it works, we're going to just use it on our image neural network here. And we are gonna do it, yeah, I'll explain that later. Make a class. The inputs to the constructor would be basically the same as the inputs here, right here. So we'll have number of inputs, number of neurons. Are we using the bias, number of samples, and then we're gonna have one extra value called rank, which was that rank value that I was right here that we alluded to, and I said it was those, and I'll show you. This right here, that dimension was the rank dimension. I'll just leave that graphic there. Probably need it again. Okay, so we got that. We'll have the number of inputs, number of outputs, which will be the number of neurons, but we'll just call it that. Bias, number of samples, and that rank. We'll have a forward method we're gonna have the backward method. Have the output, the inputs, derivative of the inputs, and the biases. And then we'll have the matrices for the weights of A and the weights of B. The biases, if we want to use that. Layer bias, which will be set equal to the bias. And then of course we need the derivative of the weights. The copy of the inputs to use on the backward method. I'm actually gonna do one extra method. Let's see. Call it big back, and it's basically it's gonna be showing the more intuitive way of doing the backward method, and then our backward method will be a more sped up way, uses less memory kind of way. So we'll do the big back first, just to show what it's like, because it's a lot more complex to do the gradients of this rather than the standard dense layer. So yeah, but first I'm just going to copy these. Samples is equal to num samples. Layer bias equal to bias. Let's just put that as R actually. Did I put rank up there? Yeah, it's right there. Okay. Allocate for the A weights matrix and the B weights matrix. Just kidding. We will randomize WA and you can always play around with these values that you're going to randomize. I think up here we did -0.1 to 0.1. You can try that out. I think, oh yeah, I use bigger values because you're going to end up multiplying these two together, so it's going to end up creating smaller values because it's going to be this times this. So if it's everything's between negative 0.1 and 0.1, your biggest value is going to be 0.1 times 0.1, which is 0.01. You're going to add two of those together. It just gets really close to 0. So, and that probably sucks for training. I think that's why I did that. But yeah, you can always mess around with it and see. Maybe it really doesn't matter. Let's see. And then I made the b's a little smaller. Give me 1 second. Decided to sit down. Okay, so we'll allocate the derivatives as well. Derivatives of the inputs. Yeah, okay. And then, last but not least, the output. Alright, it's everything basically the same as the dense layer, except you've got these two matrices here, which are going to multiply to make up the one matrix that would be just like the weight matrix here. So we got that. We'll do the forward method. Just gonna copy in all these asserts. And you can skip those if you want. They can be helpful in if you mess anything up. Layer inputs equal to the inputs. So to get the output here, go through the rows and columns. If there's a, let's see, I made it so that the layer bias, check on the layer bias in here. Yeah, we'll do it anyways. So this is going to be slower way. So putting this if statement in here will probably slow things down, branching every time. We'll slow it down a little bit. The branches should be pretty predictable, so I would assume it would not slow it down too much. But just having that in there can slow it down a little, I would assume. Which you can test. You can certainly test when training doing it this way versus having this if statement out, which you would just have an if statement out here, like out here, and like if you're doing a layer bias, do this section of code with this part. Else you would have this whole section of code with just this part. So it would be separate down here. But we're just going to leave this right here. And then we put in the multiply the weights. Now I'm trying to remember, did we use a double? Okay, no, we use floats. Okay, so that'll be a float value. It will probably say these are all wrong. I guess we'll find out if that comes up with a problem. This is the same, initializing it to 0. So that's the same as doing this equals to 0. 0f. So we're gonna make a variable total weight, which will be, we'll use another for loop. I'll just code it out and then I'll explain it. Okay, yeah. So set the output equal to the bias if we're using bias, otherwise set it to 0 so we can add to it with the dot product. So first we're looping through the output rows, output calls, so we can map out each value. The total weight is basically going to be these numbers here. So we're looping through and doing each one of these, calculating each one using these guys. So this first value would be this times this plus this times that. So looping through each one of these, so every one of the output values, and then in here is where we let's see, so these first three are just like the dense layer. You take 3 to make a matrix multiple of the inputs and the weights, and this fourth one is where we are multiplying these guys together to create the weights. So total weight k less than rank, because multiplying and adding across the rank. So each one of these values is total weight calculated by this, basically a matrix multiplication here. Go through, create this weight value there, and then the output is doing the matrix multiplication. See, we're in this one here. That is where you do the matrix multiplication, kind of the multiply and add the inputs and the total weight values. Hopefully that makes sense. This part will match well, I guess we'll go to mat dot. So that part would match this part. And this second value is the weight value right here, which the inner for loop that would have been inside here on the Lora calculates this value each time using those two smaller matrices. Hopefully that makes sense for you. If not, let me know. Any questions, whatever. Okay, so we got that. That would make the forward. That would make the forward pass. And then, yeah, so that's actually the simple part. The more complex part is the backward pass, which I'll actually end the video here, and I'll do the backward pass in the next one.